Good morning and welcome to this webinar. Thank you for attending. So in this webinar, we're going to be going over the newest features of DX Plus. We'll be taking a deep dive into those features and specifically the features that we used at the Notre Dame Power and Propulsion test that was performed in late September. In late September, Apex was involved in a hypersonic inlet test in a joint effort with AFRL and Notre Dame Power and Propulsion. The test took place at Notre Dame Power and Propulsion's state-of-the-art test facility, and we were successful in performing that test with the DX Plus software. During the test, we were utilizing hardware similar to what you see on the desk. So first is the MECOC device. This device was being used with its Wheatstone bridge card for inputs of coulites as well as strain gauges and accelerometers. The data rates for this specifically during the test was 50 kilohertz. The capabilities of the card can go up to 204.8K. Additionally, we were looking at static pressures. While we were not using explicitly a scan-about device, we're using something similar to it. So something similar to what you see on the table. The static pressures are being used and fed to Safran's CIRES data distribution platform, and we were receiving the data through CIRES. All right, so I'm just going to go ahead and start looking at DX Plus. All right, so I have DX Plus running, and this is a similar setup to what was done at Notre Dame Power and Propulsion. So I have multiple sensors up here. I have some static pressure values. I have the CFD model loaded in the center, along with a history plot of the computed critical pressure that's being done for the modeling. Additionally, I'm also doing some average pressure calculations directly in DX Plus, and then the pressure limits for the model is being referenced by these two temperature references. So these are being used as signals for the specific boundary conditions for the CFD model. To demonstrate some of the additional capability, we are not limited to just CFD. We can do structural models as well. So in this page, I have data being read from a recorded data file that's being played back as if it's a device. We see the strip chart of the computed critical pressure for the part that's being read from the strain gauge. We have a scope plot of the specific strain gauge as well as the FFT plot for it as well. And we can take a look at the model, and we can rotate and look at specifics of the model itself. Additionally, I have data coming in from a CIRES system. I have a grand total of 1,500 data channels from CIRES. Displayed in this chart are 180 of those values, and these are just coming in, and we're displaying these as text objects. So a similar setup was used at the Notre Dame test, where we had a page dedicated to static pressures that were coming in from CIRES, as well as facility values as well. And then the last page on this is displaying a strip chart of 5 of the pressure sensors that are coming in. the reference temperatures as a graphical display, as well as an LED display for the different current pressure values. So in this display at the Notre Dame test, we had an array of static pressures in the LEDs, and we were trying to arrange those based off of axial location, so that we could look at the specific values for each pressure sensor axially along the part. So one of the features that I'll go over is the new freeform plot layout. So in the freeform plot layout, we can create individual plots. So for example, I can do a magnitude envelope plot, and this gives me freeform range to size the plot, move it around. And this gives the user the capability to actually create a dashboard for their measurements, so that they have the explicit view that they are wanting. Every view is also able to be saved and loaded back in. We also support a wide range of graphic plots. So if I were to create a graphic plot for this strain gauge value, I can choose from text, a gauge, LED, or thermometer. So I can choose text here, display that, then move it around. Additionally, I can select multiple data channels, add that to the value, and create a group of sensor values and move that around as well. The freeform layout, we are also able to add a background image. So a background image can be loaded, for example, a diagram of the physical part or of the facility can be added. And by doing this, the widgets can be directly overlaid onto the image for display for the sensor that they're explicitly representing. To go over the DAT control tab. So the DAT control tab is the primary tab for controlling the data acquisition. So we have the main start and stop button for starting and stopping the acquisition, as well as the recording, data point or data events, metadata controls, and then we have the layout of the pages. So every page that is created in DX Plus, you have a representation of that page available to you in this page status window. If limits are set for the individual channels, if any item is over limit, one of these pages will display yellow or red, indicating that something on the page is approaching or over limit. We can directly switch to that page of concern. If you hover over the page, you will get the layout of the plots that are on that page. And if one of these plots are approaching or over limit, you will get the exact plot that is at that condition in this view. This view can also be popped out, and we can display this on a separate screen and kind of monitor our page statuses in an overall view, looking at their specific layouts. The additional information on this page or on this tab is for the storage usage. So this keeps track of the available space on your disk, as well as your current write rate. And additionally, it will give you the performance of your system. So indicating if the application is using too much RAM or what the CPU level is for this specific application, as well as the network bandwidth being utilized. In the Notre Dame test, we had a total of 4 displays. So each page that we have here is able to be popped out individually and moved to a separate screen for visualization. So you can see here I have a page popped out so that I'm viewing my structural model, And in the background here, I'm still viewing my CFD results being displayed. Once we close this window, it pops back into the main application and is available to you there. To kind of go over the DX Plus architecture, the DX Plus in general was developed in an API first approach and ultimately provides a testing platform, not just a single function system. This provides to the user complete customization and customized added functionality. And it also includes in the APIs the capability to access the structural and the CFD simulation data. This application is able to combine high and low rate data in a single instance, and all the data is synchronized based off of timestamps. So we're not blocking data, we're resampling data. We take the data at its native rates from device, and the timestamp occurs directly on device, and the timestamp for that data is saved with the data packet we received from the device and carries forward through all the processing routines down to data record. This is ultimately how we're performing the synchronization for the data. To best look at this, we can take a look at the designer. So this is the design that was used or that was created to display the data that we've been looking at. So I have a simulator device that is being used for our static fit. The static fit is being used to compute the fitness for the sensor values as it relates to the analytical models, and provides that to the model itself for scaling. Additionally, we have the signal math component. This is a new feature in DX Plus, to where we can add individual operations for performing math operations on the signals themselves. In this example, I'm just performing an average temperature and average pressure. If I double click on one of these, we should see the settings for this. So taking the values for each sensor and just computing an average for it. Additionally, we have Sires running. So from Sires, I had indicated here, I have 1,500 channels coming from the Sires system, and just being fed to the viewer for data viewing. Any data coming from the Sires system can also be brought in and performed for signal math or do additional processing. The last item that I have is data coming from an RWX file. The original signals are in KSI. We convert it to PSI, perform an FFT, and then go into a modal fit processor. This processor performs the mode fitness similar to the static fit, except looks at the modal solutions and computes the fitness of the individual mode that is being detected from the FFT results, and provides the fitness and the contribution factor for each mode to the model itself, so that the model can be rendered in live time. Every item that you see here on the DX Plus design page is a component that is created using the DX Plus API. So any added functionality that is added from Apex or by the customer themselves, utilizing the API, their custom functions will be available to them in this ribbon panel to be able to be dragged down and connected to other data sources. DX Plus is also developed as a distributed data platform. So not only bringing data into the application for processing and storage, but also being able to transmit the data out onto networks so that multiple clients can also view the data. So to do this, we have the DX Plus net transmit and the model transmit. Both of these are using an open standard protocol to be able to transmit the data. So any data that's transmitted can be received either by using the DX Plus API or directly interfacing to the data itself using the standard interface. To best demonstrate this, I have the DX Plus remote viewer. Then I can connect to the DX Plus instance. So once I click connect, it will connect and it will bring in all the data that's available to me for plotting. So at the moment, I am displaying, or I am publishing all the data out, but this is not required. Individual data in DX Plus can be specified as being publishable to a specific port, so that you're only publishing data that you want external users to actually be able to view. So to create a plot, we select an item, we bring it over, we select the plot type, and display the data here. Additionally, we can connect to the DX Plus model transmit. So the data being transmitted for out of the static fit and the modal fit is being transmitted through the model transmit function here. And that's being available on this port available here. All right. So once the data is being able to be retrieved from DX Plus, we can simply open up a model. We can set the solution to new bar here. Drag over the results, to which it will connect, and now we can see the model displaying here. So this provides a modeling capability not only to the DX Plus instance, but also to the clients as well. So now for data recording, all the data is able to be recorded, and we are recording it to an SQLite database. So the database is an SQLite database that's displayed here. Here we're performing data monitoring. So in the viewer, if we go to our DAC control tab, we can hit record. It will indicate that it is currently recording. In addition to this, we can also indicate we can record specific events. Now, the data being recorded is constantly being recorded to the database itself. The events that are performed are just time tags in that database in a separate table. So there's no switching of data, there's no switching of files needed, and the possible loss of data at that point. So I can set the data point number, a specific flag to it, or I can customize an individual flag here. Additionally, I can add metadata to the object. So all the standard metadata that is usually available for testing. In addition, I can add specific additional metadata to it by key value pair that is saved in the database as well. Additionally, I can also add notes for every data point that I take. Notes are recorded in the database metadata as well. So whenever the data point recording event occurs, the note that I specify for that will be available. We initiate an event recording by using the event button here. It's indicated to us that the event is recording. We can go to the next one by using the next toggle. You can see that the data point number increased. And then once I stop the data point recording, we go back into standard recording mode. And then I can end the recording altogether. So one item to note is the database itself. So why use a database? To be able to handle multi-rate data in standard flat files, the only way to be able to perform that is to record each sample rate in its own file, or every channel in its own file. And the ultimate result of that is a very large amount of files that are being recorded from your data system. Afterwards, to be able to post-process, you would need to merge all these files together in some post-processing application and basically know what is in them, or have some post-processing application be able to read their metadata and also support their specific file formats. By using a database, we're able to record all the data in a single file instance, not only just all the data, but multiple data records from the day as well. So your result is getting a single file containing your entire recording record that was performed during your test. The benefit of this is that all of your data is together. It can be post-processed together. It minimizes the amount of files that you have to sift through. In addition, it also allows for queryability. So we can query the database for specific data records, specific time ranges, or we can query for the metadata that we saved in the database as well. So, for example, the test operator name, the test cell that the test was performed in, things of that nature. Let's stop that. So to display this, we've got the DX Plus file viewer. And I'll go ahead and open up a database that was recorded. So this database that was recorded, I recorded multiple data records, and we can see the data records here. We also being recorded were the results from the static and the modal fit results. So we have that data available to us as well. So the benefit of that is where I can create the time plots for these sensors here. And we can play through those. We can see the exact values for these. Additionally, we can bring in the model as well. So here I'll bring in the CFD model. So we have the CFD solution. We'll set the solution to new bar again, be able to display this. And now once we have the model available to us, we can bring over the results, and we can play through the data. So now, right now, it's just allowing us to play back individually, but since we're timestamping the data and we're using the timestamps for data synchronization, then we can connect all these data plots together for time synchronization. To do this, we simply click this action here to time sync. We'll see that the playable bar is up at the top. At this point, we can play through the data as well, and everything is time linked. And I can drag through, and we can look at the data specifically, go to a specific time range, and be able to correlate the data together. So now the last section that I want to cover for DX Plus before we go into reviewing the Notre Dame test is basically how we're getting to the model state. And whenever we review the Notre Dame test, I'll kind of cover some of the specifics more. But if I look at the model, what was done in the test itself was, so we had some pre-test set up. So the very first thing that we had to do was after the simulations were run, we loaded the simulation. So the way that the modeling works and that the solution fits work is all based on the virtual sensors and their limits definition. So based off the sensor locations that were determined for the specific part itself, we were able to map virtual sensors for the parts. So we create a new sensor, we add it to the part, we can display it, we can see the sensor here. So now right now it's a strain gauge, but if I open up this panel, then I would be able to change the type of the sensor itself. So we can do displacement sensor, pressure sensor, temperature sensor. And each of these sensors correlate directly to their solution data. So based off the solution data, the limit information for the sensor is able to be generated out into a standard file format for use in DX Plus for computing the overall fitness correlation, as well as the contribution factors for the model itself. And again, I'll go into the specifics of this in a moment. But the sensors are essentially ratioed, so their sensitivities are ratioed to a user-defined condition. So this condition can be boundary conditions, such as max pressure, inlet pressure, and if you have multiple data solutions, then your boundary conditions for each solution can be used as a reference parameter for each limit condition. So the ultimate result of this is creating a reduced order model by utilizing virtual sensors for your overall CFD solution or structural solution, so that in DX Plus we can compute the fitness correlation as well as the contribution factor for the solution itself. All right. So that should overall complete the overview for the DX Plus features. So at this point, I'll go ahead and go into PowerPoint, and we'll take a look at the test results here. So as a review, some of the features at a glance, DX Plus provides a system and facility integration. So in the Notre Dame test specifically, we're able to use the CIRI system to bring in both the static pressures from the test article as well as the facility pressures, temperatures, PLC states, and the like. And we're able to integrate that directly with the high rate data coming from specifically the MECalc device in this test, and handling rates on the upwards of 50K to 200K, and be able to utilize that with the lower rate data. The data rates from the UND test coming from CIRI's, where it was at a 10 hertz rate, and we were handling that at roughly 400 channels. DX Plus is also database centric, so the recording is primarily meant to record to database. As of the upcoming release, that will be primarily SQLite, but we also have capabilities of interfacing with database management systems such as Postgres. DX Plus is an open architecture, so users can record, view, process homegrown systems and also add in custom processing methods, and ultimately can be in the language of choice. So this can be in Python, C#, C++, etc. And then lastly, we can integrate in with the real analytical models, both in real time and in post-processing. So we're able to view the CFD as well as structural simulation results, and correlate them with live sensor data and the sensor data from post-processing. This is a high-level view of the DX Plus architecture. So just as a review of what I previously went through, DX Plus, we have direct inputs that we have implemented ourselves, having direct connections to hardware vendors such as MeCalc, DataTel, and ScanAvalve. We also support the integration of modeling and video, and then other DAC systems. So this includes CIRES, NXDAS, IDDS, and ultimately whatever system the user would want to integrate. We can support auxiliary systems, so the data can be both exported and import from other systems, such as Python scripts, a remote DX Plus instance, as well as other DAC systems. We provide direct outputs to store data directly to database, supporting Postgres and SQLite. And then we're also supporting RDBX and HDF5 files for conversion of from database to file itself. And then ultimately the DX Plus network. So all the data being published can be published out onto the DX Plus network, utilizing an open protocol that can be used by individual users or other applications. So Notre Dame Power and Propulsion test, again, was a joint effort with Notre Dame Power and Propulsion and AFRL for testing of a hypersonic inlet. So ultimately, the successes that we had is we were able to test and validate a hypersonic inlet test article in a direct connect methodology. We were able to integrate multiple systems as we displayed. We were able to show the live CFD results to compare the sensor data. We ultimately recorded over 150 gigabytes to database, which I believe the 150 was a result of I think two hours straight of recording all the data, and we were able to synchronize and monitor high-speed Schlieren data. So we also had a high-speed camera that was being used during the test to view the flow and using a Schlieren methodology. So we're able to view that in live time, but also we're able to take the recorded video files and time synchronize with those as well. This was the processing setup. So this is similar to what we displayed for in the demonstration. So we had CIRES. We were doing some EU scaling operations to convert from degree C to Kelvin, from PSI to pascals, mainly so we could more correlate with the results from the CFD solution, given that the CFD solutions were in SI units. And then we are also integrating the MeCalc device, bringing in data which was volts from device, converting the volts to PSIA for the coulites, performing an FFT on that data, and then we also had accelerometer data that we were converting into Gs, and then performing an FFT, as well as a strain gauge that we were converting to strain units, microstrain units. We were saving the data into SQLite databases, and then we're viewing the data as well as publishing the data for modeling as well. This is a display of a model of the test article. So and the virtual sensors that were mapped to it. So we had multiple virtual pressure sensors and temperature sensors that we mapped to the model, and we were able to read their interpolated values for their locations on the solution. We had a total of 10 CFD solutions that we went through, each with a varying PTN condition, and we were able to generate the limits for each of those for use in DX Plus. The limits generation, so the limits are generated for each simulation condition. So as I said, this one was a varying PT in condition. So the pressure for the input of the inlet, and then we create a sensor array for each condition. And normalize it to a user-defined value. And in this case, we were normalizing it to max pressure for the given solution. So in calculating the fits, the sensor data provided to the static fit processor, what we ultimately ended up, or how this ultimately works, is that we take the vector of the analytical results normalized to the maximum pressure, as well as the measured pressures normalized to maximum pressure, and then we look at the similarity of those vectors, and the similarity value of 1 indicates that we're at a perfect match. A 0 is unsimilar, and then the -1 provides that we are similar, but we're in opposite directions. For the structural solutions, we're doing basically the same thing, except we're using MAC computation for the modal assurance criterion basis. The model was loaded into DX Plus, and we were able to connect that directly to the data coming from the model viewer, which allowed us to actually utilize the contribution factors for the scaling of the model solutions themselves. And then just as a review for the overall test setup, we had static pressures going into a net scanner, as well as thermocouples going through a VTI device, which ultimately was going through CIRES, and then CIRES was supplying that data to DX Plus at a 10 hertz rate. In addition to that, we also had facility measurements coming into us through CIRES as well. The MECOC device was handling the coolites, the accelerometers, and the strain gauge. We were bringing in the CFD results, and we were also bringing in the Phantom camera live display and recording the data to the SQLite database. Some of the images from the test. So we have ultimately the control room with multiple engineers using DX Plus simultaneously, looking at the data being displayed for DX Plus at Notre Dame Power and Propulsion. Next, we have an image of DX Plus running itself. So again, we have the four main displays with various plot windows popped out for monitoring, as well as visualization of the Schlieren data itself. Next, we have a picture of the Phantom camera being utilized. So this was the camera being used for the Schlieren. The video was being recorded at a 10 kilohertz rate on camera. Then lastly, we have the test article. So while we can't show the test article in its full visibility, this is a cropped picture of it showing the test article with the mounted static pressure sensors and coolites that was on the article itself. All right, so what's next? So we're currently in way of post-processing the data from the Notre Dame test and providing an overall report. Next, we have a free jet test at AFRL ADC. This test will be utilizing the full four-body 3D printed in a free jet test cell. That test should be taking place sometime in January. And then we have DX Plus release that is scheduled for end of year. Ultimately, we're continuing the development of this, and we would like additional feedback for features that customers are looking for, specifically for hypersonics or structures, or ultimately your testing scenarios, because this project, or because this software platform is wide ranging of capability. So we are looking for feedback from users to what would ultimately make testing easier for them. All right, so I think that overall ends the webinar, and I think at this point we will take some questions. All right, so I do have a question here for the custom processing. To what extent does Apex need to be involved, if at all, to implement custom processing elements? Can these custom elements be shared easily in my organization? So Apex does not have to be involved. We're able to supply the SDK to the customer. The customer is able to implement it themselves, and through their implementation, their custom capability will display in the DX Plus application. So ultimately, Apex does not have to be involved, though we can provide support if that's needed. Okay, so I have a comment here about the applications that might need a high-speed camera. So in this test specifically, we're utilizing a high-speed camera for visualization of Schlieren data, but this can also be used in structures for spin pits, for visualizing the crack formations, being able to correlate that directly with the recorded data itself, and be able to step through the visualization frame by frame, correlating that with the data itself. Also, we've also been in discussion with other vendors of utilizing high-speed cameras for image-based strain computations. So that's another area that is being looked at as well. Okay, so I have a question here. If there is a way to trigger event recordings increments using a 5-volt trigger or similar. Yes, though that feature specifically is not scheduled until most likely Q1 of next year. So we've implemented methods that we've denoted as automations, so that a specific signal or trigger signal can be monitored in DX Plus itself, and once that trigger occurs, then it automatically begins a recording event. All right. We've got another question. If we have a setup with DS, would both DS computer and the DX computer need to be on, or would the DS program run on the DX computer as well? How do we integrate our older system into DX Plus? So DS and DX Plus can be run together. They do not have to be on the same system either. If you're wanting to bring in data from DS and be able to store that in a database with your other data, then we've provided DS as an input to DX Plus. So in the same way that you would use DR to connect and visualize your data in a remote client, DX Plus can connect to DS, receive the data. You can perform further processing in DX Plus on the data being received from DS, or you can just directly store the data from the DS system into the database itself. All right. Were there any unique takeaways from the test at Notre Dame? So ultimately, so for some of the things that we learned were dealing more with the camera itself. We did have some issue triggering the recording on the camera, so we're in active development for that, and supporting that. So we had a feature where recording event would also simultaneously software trigger the camera for recording. So we did discover an issue there that we're in current implementation. Some of the ultimate feedback that we got is that having the visualizations move to be more test article centric rather than just specific signals themselves, and introducing the modeling basically provides faster turnaround for post-processing and is able to direct the focus for the post-processing itself. I think that's the main items from what I remember there. I have a question on the hardware that I have displayed. So this on my left, as we went through it at the start, is the MeCalc device. So this is a MeCalc DecaQ system. In this system, we have multiple Wheatstone bridge cards that supports user selected functionality for voltage input, ICP input, as well as bridge input. MeCalc offers a wide range of acquisition cards for voltage, ICP, bridge, high rate inputs, TAC cards, and all of them can be provided in the system and exchanged or swapped out in the system as well. On my right side here, I have a DSA 5000. So this is a pressure device from Scanavalve. So this provides static pressures. I believe that the rate for this can go up to 10 kilohertz rate for pressure measurements. Okay, going over DX Plus and handling of time synchronization. So time synchronization of DX Plus, it occurs using the absolute timestamp that is the timestamp that's provided from device. So the majority of the hardware platforms that are coming out now support PTP that ultimately provides up to or around a 300 nanosecond accuracy value. So DX Plus brings in the data from, for example, the MeCalc system, which is also providing that when the samples were taken, provides the timestamp of the samples, and that we bring that into the system, and then that timestamp carries all the way through. The Scanavalve is the same thing. This is PTP synced. So this system also provides the timestamp of the data that's retrieved from the system, and that timestamp carries through with the data through the processing pipeline. For systems that do not support PTP, there are a few options. So DX Plus does offer a time synchronizing component, which will utilize either a user-defined offset if a time offset is known, or an iRig signal. So for devices that do not support any time stamping, then an input channel of the device can be utilized with an iRig input, and then using the iRig signal for that device, the time stamping for the data coming through will be based off of iRig time at that point. So ultimately, no matter what the sample rate is, we're able to use the timestamps of the data to align the data with other devices, and that's how we're performing operations such as signal math, how we're performing rev resampling, and plot correlation. So plotting low rate data versus your high rate, utilizing the native rate at that point. All right, next question. is the most efficient way to apply scaling coefficients, EUA, EUV, for sensor groups with multiple instruments that have different calibration functions. So the DX Plus provides a EU scaler, and this ultimately provides the ability to apply a polynomial scaling factor to the incoming data. So by default, it's linear, so it's the EUA, EUV. However, you can apply quadratic or cubic functions to it to scale your data coming in from your device. The EU scaler, it applies the same scaling factor to a group of measurements that are brought in. So if you have multiple calibration factors, you can have multiple EU scalars. Additionally, we're also adding the function for being able to read in scaling factors from an external source, such as a CSV, to be able to apply them to the data itself. If database recording is not used, then each channel will be saved in its own file. So that comment was more geared towards legacy systems or current systems that are using flat file formats. So to be able to handle multiple sample rates, the traditional way to do that in recording flat files is either have a single file handle a single sample rate to where all your channels for that sample rate are recorded to that file, or each channel is saved in its own file. So an example of this is the DATX file format. So the DATX, a single file cannot handle multiple sample rates. However, they provide an index file and then a group of other files that either you have a group of signals being written to the same file for a given sample rate, or there's options for writing out data as individual channels or a channel per file. And by shifting that to being a database centric, all your data is able to be recorded together, and then based off a query, you can export to other file formats or other storage options. Okay. All right. Well, we'll go ahead and end the event. And thank you for joining today, and thank you for staying with me as we went through the DX Plus capability. If there are any questions that come up, you are free to email us. And I believe that this webinar will also be available as a recording at some point as well. All right. Thank you.